I want you to start by picturing a very specific, like almost universally uncomfortable sensation.
Oh boy. Okay.
Just imagine you are holding a raw, intensely acidic lemon wedge. Like we're talking about one of those heavy, bumpy, bright yellow lemons that you just know is absolutely loaded with sharp, burning citric acid.
Right. The ones that make your jaw ache just looking at them.
Exactly. So you bring it up to your mouth, you bite down hard right into the center of the pulp, and you wait. Your entire body braces for it.
Yeah, you're waiting for that involuntary shiver to run down your spine.
Right. You wait for your lips to pucker, your jaw to clench, your eyes to water, because, I mean, your brain knows that what you just put in your mouth is practically battery acid,
Well,
right?
yeah, and it's a deeply ingrained biological defense mechanism. We have evolved to violently reject unexpected, highly acidic substances.
Because acid usually means danger.
Exactly. In the wild, extreme acidity often correlates with unripe, spoiled, or potentially toxic food. Just think about the visceral, full-body rejection you experience if you accidentally take a gulp of spoiled milk.
Oh, gross. Yeah.
The lactic acid hits your tongue, and your nervous system practically screams at you to spit it out.
It's an alarm bell, but what if you bit into that lemon and the alarm bell never rang?
That would be, well, that's deeply unsettling.
All right. What if instead of puckering your lips and grimacing, it tastes like pure, unadulterated honey? Like it tastes like a rich, perfectly ripe peach dripping with syrup?
Wow.
The sheer physical impact of the acid just vanishes, and you are left with this overwhelming, intoxicating sweetness.
I mean, that is an incredibly jarring psychological experience.
Yeah.
Your brain is fully anticipating a hostile acidic assault, and when that assault never materializes, it creates this profound sensory dissonance.
Exactly.
Because the physical substance in your mouth hasn't changed at all. The lemon is still a lemon. But your brain's interpretation of it has been entirely rewritten.
And here's the crazy part. This isn't some parlor trick. It's not a hypothetical thought experiment or a placebo effect. It is a literal biological hijacking of your taste buds.
Yeah, it's caused by a very real, very peculiar West African plant known as the miracle berry, or Synsepalum dulcificum, if we're being formal.
So today we are putting on our lab coats. We're stepping into the shoes of sensory scientists for this deep dive.
I love it. Let's do it.
Our mission today is to dissect the exact atomic level molecular biophysics of how this tiny red fruit pulls off this illusion. Because once you understand the mechanics of this berry, it completely shatters what you think you know about human reality and perception.
It really does. And to map out that mechanism, we are drawing from a truly massive multidisciplinary stack of sources today.
We've got a lot to cover.
We do. We are looking at comprehensive structural analyses of glycoproteins, historical botanical journals stretching back centuries, magnetoencephalography, or MEG brain scans that map the cerebral cortex in real time.
Which is wild stuff, by the way.
It's incredible. And we're also pulling from some groundbreaking chemical sensory research from universities across the globe.
Okay, let's unpack this. The best way I could describe this to a friend was to compare it to like a sensory Instagram filter.
Oh, that's an interesting way to put it.
Yeah, like if you think about taking a photo of a bleak gray, cloudy skyline, right? The physical reality of that city doesn't change, but you apply a bright, warm filter to the digital data, and the final image that renders on your screen looks like a sunny summer day.
Right, right.
The miracle berry does exactly that, but it is rewriting the biological data that your tongue is transmitting to your brain.
That's a highly functional analogy, actually.
Mm-hmm.
The physical reality of the food, so the chemical composition of the lemon juice or the vinegar is completely unaltered,
Right.
but the biological rendering engine of the tongue is flipped. However, before we start looking at the microscopic rendering engine itself, we really need to understand the macroscopic subjective experience of this fruit.
Yeah, we have to look at the history and just the sheer weirdness of the phenomenon first.
Right, we have to start with the origins, because from what I was reading, this isn't some new genetically modified organism cooked up in a Silicon Valley lab.
No, not at all. Synsepalum dulcificum is an evergreen shrub native to West Africa. And local populations have known about its bizarre properties for a very, very long time.
Centuries, at the very least. The first major documentation of the plant by a European observer occurred in 1725.
1725.
Yeah. There was a French explorer and cartographer named Chevalier de Marchais. He was on an expedition mapping the coast and observing the cultures of West Africa, and he noticed that the local tribes had a very specific, deliberate ritual before they sat down to a meal.
Right, they weren't just eating the berries as a snack.
No, it was entirely preparatory. The traditional diet in that specific region at the time heavily featured intensely sour foods. So we're talking fermented palm wine, highly acidic pit fruits, sour cornbread.
Stuff that really makes you pucker.
Exactly. And Desmarchais watched as the locals would take these small, unassuming red berries, which are roughly the size of a coffee bean, by the way, and they wouldn't just swallow them.
Oh, they chew them.
Yeah, they would chew them methodically, ensuring the pulp coated the entire inside of their mouths before they started eating the actual meal.
They were essentially prepping their palate, like they were hacking their own meal.
That's exactly what they were doing.
And fast forward 300 years. This exact same mechanism is the centerpiece of what people now call flavor-tripping parties.
Yes, those have become quite popular.
Have you heard of these? You go to one of these events, you chew a freeze-dried miracle berry tablet or the fresh fruit, and then you just go to town on a buffet of the most aggressively bizarre sour foods imaginable just to see how they taste.
The contrast is what makes the experience so striking. And the sources detail some truly wild sensory conversions at these parties.
Oh, the reports from these taste tests are unbelievable. Like, people will drink a heavy, dark, bitter Guinness beer, and they swear on their lives that it tastes identically to a rich, sweet chocolate milkshake.
A chocolate shake beer, that is so strange.
Right. Or take Tabasco sauce, which is notoriously sharp, acidic, and vinegary. Under the influence of the berry, it completely loses its sting. It just becomes this complex, sweet, smoky pepper glaze.
Which actually sounds delicious.
It does. You can literally take a shot glass of raw apple cider vinegar, which would normally make your eyes water and your throat close up, and it goes down as smoothly as sweet pressed apple juice.
Wow.
Salt and vinegar potato chips become a savory sweet dessert. Lemons, limes, and grapefruits gush with a sweetness that rivals pure sucrose.
And what researchers immediately noticed was the sheer consistency of this illusion. This isn't like a psychological suggestion where some people experience it and others don't.
It's not a placebo.
Not at all. It is a highly predictable, replicable biochemical reaction that occurs in every healthy human gustatory system. But it is entirely bound by very strict temporal and chemical parameters.
Yeah, which is lucky because as fun as a chocolate shake beer sounds, you probably don't want to be stuck tasting that for the rest of your life. So how long does the filter last?
It is relatively fleeting. The effect requires the pulp of the berry to physically bind to the epithelial layer, so the outer cellular surface of the mouth and tongue.
Okay, so it sticks to your mouth.
Right. And once that binding occurs, the illusion lasts anywhere from 30 minutes to about 2 hours max.
So what breaks the bond? Does the body just eventually recognize it as a foreign substance and clear it out?
It's actually a passive process driven by your own digestive biology. Your saliva isn't just water, It's a complex fluid packed with enzymes.
Right, salivary amylase.
Exactly, primarily salivary amylase, which actively works to begin breaking down food the second it enters your mouth.
Oh, I see.
So over the course of an hour or two, that continuous wash of amylase and swallowing literally scrubs the miracle berry proteins away from your taste receptors. It washes them down your throat and returns your palate to its baseline unhacked state.
Okay, but as I was reading through these clinical sensory trials, I found myself getting really hung up on one specific detail, a massive limitation.
The acidity rule.
Yes. The sources are incredibly clear that the miracle berry only affects acidic foods, foods with a low pH, meaning if I chew a miracle berry, wait 5 minutes, and then eat a piece of raw broccoli, which is bitter, it still tastes exactly like bitter broccoli.
Right. No change whatsoever.
If I eat a regular salty cracker, it just tastes like salt and carbs. It does absolutely nothing to bitter, salty, or umami flavors on their own. It only acts as a bridge from the sour sensation to the sweet sensation.
This is a very narrow bridge.
Yeah. Why is this biological hack so incredibly specific to acid?
Well, that specificity is the essential clue to understanding the entire mechanism.
Okay.
And to answer why it only targets acid, we have to zoom way in.
Put on the microscopic lenses.
Exactly. We have to transition from the macroscopic subjective experience of eating the berry down to the objective microscopic chemistry. We have to look at the molecule itself.
Let's get into the how.
Yeah.
Because in 1968, researchers actually managed to isolate the specific active ingredient in the fruit, right?
They did?
And they gave it a very fitting, if somewhat uncreative name, Miraculin.
Miraculin, yes.
Yeah.
Botanists love to just add IN to things.
Right. But from a chemical standpoint, Miraculin is not a simple sugar like glucose or fructose. It's a massive macromolecule. Specifically, the literature classifies it as a glycoprotein.
That's right.
Let's break that down for everyone. A standard protein is basically a long chain of amino acids, right? The building blocks that do all the heavy lifting in our cells.
Correct. Standard proteins are organic compounds made of amino acids, which contain nitrogen, carbon, oxygen, and hydrogen that fold into complex 3D shapes to create enzymes, antibodies, and muscle tissue.
Okay, but a glycoprotein is a very specific subclass.
Yes, the prefix glyco refers to glucose, or sugar. So a glycoprotein is a protein core that has oligosaccharides, which are complex carbohydrate chains covalently attached to its outer surface.
So to visualize it, it's essentially a massive protein block wearing a thick coat of sugar molecules.
That's a great way to visualize it.
Yeah.
And the body uses sugar-coated proteins all the time, often for cell-to-cell recognition or immune system functioning, because those sugar chains act like intricate molecular ID tags.
Oh, that makes sense.
In the case of Miraculin, the core protein consists of a specific sequence of 191 amino acids. And attached to the sides of this amino acid chain are several distinct sugars: glucosamine, mannose, fucose, xylose, and galactose.
It is a serious sugar coat.
It is. These carbohydrate chains make up about 14% of the molecule's total weight.
Okay, 191 amino acids plus a 14% sugar coat. That sounds enormous compared to a simple molecule like sodium chloride, which is just 2 atoms.
It is an absolute behemoth of a molecule.
And the sources point out that Miraculin belongs to a very specific structural family known as the Kunitz-type soybean trypsin inhibitor family, which frankly sounds like a random assortment of scientific buzzwords. Let's demystify that.
It is a mouthful, I admit. But it simply refers to the evolutionary lineage and the 3D folding pattern of the protein. Proteins don't just exist as straight lines.
Right, they bunch up.
Exactly. They fold up into incredibly complex origami-like shapes based on the magnetic attraction and repulsion of their amino acids. Proteins in the Kunitz-type family typically fold into a structure called a beta trefoil fold, which kind of looks like a 3-leaf clover made of ribbons.
Okay, a 3-leaf clover. I can picture that.
Now, natively, proteins in this family usually act to inhibit digestive enzymes in the gut, like trypsin. But evolutionary biology is incredibly resourceful. Miraculin shares this basic 3-leaf clover shape, but over millions of years, this West African shrub mutated and repurposed that shape to perform a completely different function on the tongue.
And it doesn't even operate alone. The sources emphasize that its native state is a homodimer.
Yes, a homodimer.
So breaking down the root words, homo meaning same, and dimer meaning 2 parts. Basically 2 identical puzzle pieces snapped together.
Precisely. You rarely find a single Miraculin molecule floating on its own. 2 of these 191 amino acid chains link together, and they are bound by a disulfide bridge, which is a highly stable, strong covalent bond between 2 sulfur atoms.
So they are seriously locked together.
Think of it like a steel rebar connecting 2 blocks of concrete. Sometimes 2 of these dimers will even link up to form a tetramer, a massive 4-part complex.
But despite being this huge sulfur-linked, sugar-coated macromolecule, it's incredibly fragile, isn't it?
Extremely fragile. It is highly thermolable.
Thermolable. Okay. Thermo meaning heat, labile meaning easily altered or unstable.
Right. If you apply heat to Miraculin, specifically anything above 100 degrees Celsius, which is the boiling point of water, the protein denatures.
It just falls apart.
Exactly. The heat energy causes those delicate origami-like folds to vibrate and shake apart. It unfolds, loses its 3D shape, and is completely destroyed.
Oh, wow.
This is why you cannot cook with miracle berries. You can't bake a miracle berry pie or drop them into a boiling vat of soup and expect the flavor tripping effect to work.
The structural integrity is just gone.
Exactly.
Exactly.
And it's not just vulnerable to heat. It degrades and loses all biological activity in extreme pH environments. If you expose it to a pH below 3 or above 12 at room temperature, the extreme concentration of ions tears the protein apart.
See, here's where it gets really interesting. This brings me to one of the most fascinating contradictions in the entire deep dive. People colloquially call the miracle berry a sweetener.
Oh, I know. It's everywhere.
All right, you see it in articles all the time. The ultimate natural sweetener. But reading the actual biochemistry, it absolutely is not a sweetener in any traditional sense.
Not at all.
Like, if you put a spoonful of pure sucrose on your tongue, it tastes sweet immediately. If you put a drop of artificial aspartame on your tongue, it tastes intensely sweet. But if you isolate pure Miraculin and place it on a perfectly clean, pH-neutral tongue, it tastes like absolutely nothing.
You're touching on a fundamental misunderstanding in popular media. On its own, at a neutral pH, which is around 7, The normal resting pH of your saliva Miraculin has a bland, practically undetectable flavor profile.
It's just a block of tasteless protein.
Exactly. It does not trigger the sensation of sweetness by itself.
Right. So if it doesn't taste sweet, how on earth is it making a lemon taste sweet? The analogy that kept coming to my mind while reviewing the receptor data is that Miraculin is like a key that perfectly slides into a lock, but it refuses to turn.
Oh, I like that.
Yeah, it just sits there in the keyhole, completely jammed, doing absolutely nothing to open the door until the environment around the lock magically changes.
That is a perfect segue into the actual receptor mechanics. How does this tasteless key suddenly transform into one of the most powerful perceived sweetening agents in the natural world?
It requires a trigger.
It requires a very specific environmental trigger.
And that trigger is acid.
To understand how the trigger works, we have to look intimately at the lock itself. So the human sweet taste receptor. Down in the microscopic taste buds of your tongue, embedded in the cell membranes, you have a specific receptor complex, officially designated as HT1R2, HT1R3.
Okay, the human taste receptor type 1 members 2 and 3.
Correct. It is a heterodimer, meaning it's made of two different protein subunits that clasp together to function. And this complex belongs to a massive, incredibly important class of cellular sensors called G-protein coupled receptors.
We see those everywhere in biology.
We do. We don't need to get bogged down in the deep cellular biology here, but essentially, these receptors are the sensory bridges between the outside world and the inside of your cells.
Okay, let's try to visualize the part of the receptor that is actually exposed to the food. The sources describe the top of this receptor, so the part sticking out of the cell into your mouth, as having a venous flytrap domain, or VFD.
That's a great name.
That is such a vivid name for a microscopic protein. Does it literally function like the carnivorous plants?
It genuinely does. The VFD is a hinged protein structure that rests in an open, gaping state, which biochemists refer to as freeform 1.
Okay, freeform I is open.
When a sweet molecule, let's say a molecule of glucose from an apple, floats by in your saliva and lands inside that open trap, the physical presence and chemical bonds of the sugar cause the trap to snap shut.
Like a jaw closing around the sugar.
Exactly. Snap shut into a state called freeform 2. And that mechanical closing action on the outside of the cell causes a structural shift on the inside of the cell.
A domino effect.
Right. It triggers a microscopic row of dominoes, the G-protein cascade, which ultimately opens calcium channels, releases neurotransmitters, and fires an electrical signal down the gustatory nerve to your brain shouting, "Hey, we just ate something sweet, send dopamine."
Okay, I love that visual. So let's bring Miraculin back into the mouth. You chew the berry, the massive sugar-coated protein coats your tongue, the resting pH of your mouth is neutral, right around 7. What happens at the molecular level?
Under normal, neutral conditions, the Miraculin molecule actually binds very strongly to that HT1R2-HT1R3 sweet receptor. It slides right into the venous flytrap domain.
But going back to your key analogy, it doesn't turn.
Right. In pharmacological terms, at a neutral pH, Miraculin acts as an antagonist.
Meaning it actively blocks the receptor without activating it?
Yes. It occupies the physical space inside the trap, but its shape doesn't trigger the hinge to close.
Yeah.
And because this massive molecule is just sitting there wedged in the door, it actually prevents other real sweet molecules from getting inside.
So it actually stops you from tasting sweet things.
In vitro laboratory studies show this beautifully. If you expose isolated taste cells to Miraculin at a neutral pH, and then try to feed those cells a known sweet substance like sucrose, the sweetness response is actually inhibited. It is effectively a sensory blocker.
It's a biological sleeper agent. It just sets up camp on the tongue, completely inactive, blocking traffic, just waiting.
Exactly, waiting for the environment to change.
But then it does change. You bite into the lemon, you flood the environment with a heavy dose of citric acid, or you take a shot of vinegar, flooding it with acetic acid.
And the moment that acid makes contact with the tongue, the local environment undergoes a drastic shift. The pH drops rapidly from that neutral 7 down to somewhere between 4.8 and 6.5.
Which is pretty acidic.
Now, acidity fundamentally is just a high concentration of free-floating protons, or positively charged hydrogen ions. This sudden massive surge of protons triggers a dramatic, violent chemical event on the Miraculin molecule.
Protonation.
Exactly. The protonation of the histidine residues. On the 191 amino acid chain of the Miraculin molecule, there are specific amino acids called histidines that are highly exposed to the surrounding environment. Specifically, the research points to histidine 29 and 30 and histidine 59 and 60.
Okay, so these specific parts of the protein are just hanging out there in the acid.
When the environment becomes highly acidic, The massive influx of protons aggressively attaches to the imidazole rings of these histidine residues.
So you are forcefully cramming a bunch of positively charged protons onto a molecule that was previously balanced? I imagine that completely wrecks the electrical stability of the protein.
It creates absolute biochemical chaos for a fraction of a millisecond. It introduces strong positive charges to areas of the protein that were previously neutral.
Wow.
And in the world of biochemistry, when you change the electrical charge, you inherently change the 3D shape. Because proteins are held together by very delicate balanced forces of magnetic attraction and repulsion, this sudden influx of positive charge causes the protein to repel itself in new ways.
So morphs.
It causes a massive conformational shift in the entire 3D structure of the Miraculin homodimer.
The sleeper agent receives its activation code. The protons are the code that tells it to wake up.
That is precisely the mechanism. In an instant, the shape-shifting Miraculin transitions from being a passive antagonist, a blocker, into a powerful, hyper-aggressive agonist.
And what does it do once it shifts?
The conformational shift physically contorts the molecule and forcefully drives that carbohydrate segment we talked about earlier, those heavy sugar chains attached to the protein deep into the venous flytrap domain.
So it's not just sitting in the trap anymore. It aggressively elbows its way in and forces the jaw to snap shut.
It slams the trap shut. It stabilizes the receptor tightly in freeform too. This mechanical closing of the receptor triggers the exact same G protein cascade inside the cell that a massive spoonful of pure sugar would.
That is wild.
It fires an intense, screaming electrical signal down the gustatory nerve fibers directly to your brain saying, sweet.
And the craziest part of the literature is that the intensity of the sweetness is directly tied to the intensity of the acid.
It's a direct correlation.
The lower the pH drops, meaning the more acidic it is, and the more protons are flooding the mouth, the stronger the Miraculin binds and the harder the receptor fires. It literally uses the burning acid as the fuel to power the sweetness illusion.
And it is completely reversible in real time.
Really?
Like instantly.
Pretty much. As soon as you swallow that mouthful of acidic lemon juice, your body's saliva washes over the tongue, buffering the environment and quickly returning the pH back to a neutral 7. The protons detach from the histidine residues.
And it goes back to sleep.
The Miraculin shifts back to its inactive, relaxed shape. The venous flytrap opens up and the sweetness instantly stops.
Until you take another bite of the lemon, and the cycle repeats. It just toggles on and off, based entirely on the ambient pH of your tongue in that exact millisecond. It's an incredibly elegant mechanical switch. It is a marvel of evolutionary biophysics. But understanding this mechanism brings us to a glaring contradiction, a genuine paradox in human physiology.
Right, and this is the part of the research that genuinely broke my brain. It made me reconsider everything about how I experience the world.
It's profound stuff.
If you are eating a raw lemon, you are absolutely flooding your mouth with citric acid. We just meticulously established that the acid acts as the trigger. The protons change the shape of Miraculin, making it hit the sweet button, but the acid is still physically there.
It hasn't gone anywhere.
The sour, acidic molecules haven't magically vanished from your mouth. They are still actively braining your tissue.
So, wait. Why don't we taste a sickening, overwhelming mixture of intense sweet and intense sour at the exact same time? Where does the sour data go?
To solve that paradox, we have to look past the tongue and connect this to the bigger picture of how the central nervous system processes data. And when we do, we find the most startling, almost unnerving revelation of this entire deep dive.
Okay, lay it on me. The peripheral reality, what is actually happening down in your mouth, is that Miraculin does not block your sour receptors.
Wait. Let's just pause and think about the implications of that one sentence. It does not block the sour receptors.
Not even slightly. Miraculin has absolutely zero physical interaction with the sour taste receptors on your tongue.
Wow.
The sour receptors are entirely separate cellular structures. They are specific ion channels, completely distinct from the sweet G protein receptors. When you bite into that lemon after eating a miracle berry, your sour receptors are firing at 100% capacity.
So they are tasting the acid.
They are successfully detecting the dangerous high-level acidity. They are sending frantic high-voltage electrical signals up the cranial nerves to the brain saying, warning, system alert, we are currently consuming tissue-damaging battery-level acid. Your tongue knows exactly what is happening. It is not being fooled.
Okay, so if I'm understanding this correctly, the tongue is successfully sending two massive contradictory signals up to the brain simultaneously. It's shouting, wow, this is the sweetest thing we've ever eaten, and also shouting, wow, this is incredibly sour and acidic and dangerous. But subjectively, when I do this, I don't experience the sour. I only experience the sweet.
Exactly.
If the tongue is sending the data, where is the data being deleted? How is the brain lying to me so convincingly?
To figure out exactly where the lie is manufactured, a team of researchers in Japan conducted a groundbreaking study in 2006. And to track the signals, they used magnetoencephalography, or MEG scans.
I've heard of fMRI and EEG, but how does a MEG scan work in this context?
It's an incredibly precise neuroimaging technique. Whenever a neuron fires in your brain, it generates a tiny electrical current. And as physics dictates, any electrical current generates a corresponding magnetic field.
Right.
And MEG machine uses hypersensitive magnetometers to map those microscopic magnetic fields in real time. It allows scientists to see not just where the brain is processing information, but when, down to the millisecond.
So they can literally watch a thought or a sensation travel through the neural pathways.
Exactly. So they put human subjects in the MEG machine, gave them miracle berries to coat their tongues, and then fed them raw citric acid.
Okay.
They tracked the neural signals from the exact moment the acid hit the tongue, up the cranial nerves, through the brainstem, and all the way up to the gustatory cortex, which is where conscious perception of taste occurs. What they found was the ultimate neurological deception. It's a phenomenon known as central gating.
Central gating, meaning the gatekeeper filtering reality isn't the sense organ itself, but the central nervous system.
Yes. Now, at the peripheral level, down in the taste buds, there's a very minor interaction. About 20% of the sour signal is suppressed locally, purely due to the complex way local taste cells inhibit each other.
Okay, but 20% isn't much.
No, it's not.
Yeah.
The remaining 80% of that raw, burning, frantic sour signal successfully makes it out of the tongue. It travels up the glossopharyngeal and facial nerves, and it arrives at the brainstem, specifically a region called the nucleus of the solitary tract.
And then what?
It never makes it out of the brainstem. It never reaches your conscious perception.
Because the sweet signal is just too loud.
Essentially, yes. The brainstem acts like an overwhelmed switchboard operator. It receives this massive, artificially amplified, deafeningly loud, sweet signal coming from the sweet-sensitive S fibers. And at the exact same moment, it looks at the sour signal coming in.
It has to make a choice.
The brainstem has to decide how to route this data to the conscious brain, and it actively chooses to drop the sour call.
It just unplugs the wire.
It engages inhibitory interneurons. Think of it like a live soundboard engineer at a concert. The microphone for the sweet channel is peaking. It's incredibly loud. So the engineer physically grabs the fader for the sour microphone and pulls it all the way down to zero, muting it completely just to make sense of the audio mix.
Oh, wow.
The brain actively prioritizes the sweet data and entirely deletes the sour data from your subjective conscious reality.
This is genuinely mind-blowing. Let's really process what this means. We navigate our entire lives operating under the assumption that what we see, what we hear, and what we taste is objective reality.
We all do it.
We assume our senses are like passive video cameras, just recording the world and playing it back on a screen in our minds. But this MEG study proves unequivocally that our perception is an active, heavily biased editor.
What's fascinating here is that it proves it is entirely constructed. The brain receives a chaotic, overwhelming mess of electrical signals every second, and it has to actively decide what narrative to present to your conscious mind.
Right.
In this specific scenario, because of the evolutionary priority of high-calorie sweet foods, the brain decides the narrative is sweet. And to preserve that narrative, it completely suppresses the physical, dangerous reality of the acid burning your tongue.
If our brain is perfectly willing to completely ignore tissue-damaging acidity, a clear biological danger, simply because an artificial sweet signal is a little bit louder, what does that say about how much we can actually trust our own sensory experience?
It raises a profound question about the fragility and malleability of human perception. It only takes a transient, localized shift in oral pH and the presence of a single plant glycoprotein to make your central nervous system actively lie to you about the fundamental chemical composition of the food you're actively consuming.
Which naturally brings up an incredibly practical and, frankly, somewhat frustrating question.
I think I know where you're going with this.
If we have a natural protein grown on a bush that can safely make raw vinegar taste like apple juice and make sour lemons taste like sweet candy, all without adding a single calorie of actual sugar or causing an insulin spike, why on earth isn't this in every pantry, restaurant, and coffee shop in the world?
It's the logical next question.
Why am I still putting refined white sugar in my tea when I could just chew a miracle berry? Why hasn't this completely taken over the world?
That is a fascinating question, and the answer has very little to do with biology and everything to do with bureaucracy and commerce.
Of course it does.
To understand the commercial absence of the miracle berry, we have to rewind to the late 1960s and early 1970s and look at the history of a man named Robert Harvey and the Miraculin Company.
Okay, I read about this in the sources. The Miraculin story. Harvey wasn't just some snake oil salesman, right? He was a legitimate biochemical postgraduate student.
He was. Harvey isolated Miraculin and immediately recognized its massive, world-changing commercial potential. He saw a Western world that was beginning to struggle intensely with rising sugar consumption, obesity, and the early controversies surrounding chemical artificial sweeteners like saccharin.
Right, saccharin was getting a lot of bad press back then.
Exactly. He realized that Synsepalum dulcificum could be the ultimate healthy, natural alternative. He founded the Miraculin Company with the explicit goal of bringing Miraculin to the mass market.
And from what the historical sources say, they were incredibly successful right out of the gate. They weren't a tiny startup for long.
No, they scaled rapidly.
They raised millions of dollars in venture capital. They established huge, sprawling plantations in Jamaica and Puerto Rico just to grow the berries at scale.
They had massive agricultural operations.
They were running highly successful consumer product testing. Like, people were trying Miraculin-laced popsicles and drinks, and they absolutely loved it. It seemed like the Miraculin Company was poised to completely disrupt, if not destroy, the multi-billion-dollar sugar and artificial sweetener industries.
They were on the precipice of a revolution in the food industry.
Ugh.
But then the regulatory hammer fell. In order to legally sell Miraculin as a food additive in the United States, it needed a very specific classification from the FDA. It needed to be designated as GRAS, generally recognized as safe.
Which, to be fair to the FDA, makes total sense. You don't want unregulated corporations just isolating random, untested macromolecules from exotic plants and dumping them into the public food supply without oversight.
Absolutely not. The GRAS designation exists to protect public health. However, in the fall of 1974, the FDA abruptly denied Miraculin its GRAS status.
Just flat out denied it.
And the official reasoning they provided was deeply frustrating to the company. The FDA stated that there was a lack of substantial history of consumption of the substances by a significant number of consumers in the United States.
Oh, come on.
Because it was a West African berry that Americans hadn't historically eaten, the FDA argued there wasn't enough longitudinal, multi-generational safety data to just declare it safe. They demanded exhaustive, incredibly expensive, long-term toxicological testing before it could be sold.
And that ruling essentially bankrupted the Miraculin Company overnight, didn't it?
Completely destroyed them.
They had all their capital tied up in the plantations and the extraction facilities. When they were told they couldn't legally sell their product for years, if ever, the investors pulled out, the plantations were shuttered, the plants were destroyed, the dream completely died.
It was a very sudden collapse.
But of course, a rise that rapid, followed by a fall that sudden and crushing, is the perfect breeding ground for decades of conspiracy theories.
It certainly is. For decades, many proponents of the miracle berry and critics of the food industry have loudly suggested that the FDA didn't act purely on scientific caution. The prevailing conspiracy theory is that the regulatory agency was heavily, perhaps illicitly, lobbied by the powerful sugar conglomerates and the artificial sweetener industry,
Who supposedly viewed Miraculin as a catastrophic existential threat to their profit margins.
Exactly. Now, it must be stated that these remain conspiracy theories. We have to be clear about that. There is no definitive smoking gun proof of illicit lobbying resulting in the ban. But the timeline of the FDA's sudden intervention certainly fueled the enduring narrative that Big Sugar killed the miracle berry.
So what does this all mean? It's a tragic story of innovation hitting a brick wall. The best way I can conceptualize it is that the miracle berry is like a profound technological marvel, a biological piece of hardware that could change the world that got permanently stuck in beta testing because the instruction manual was lost in a bureaucratic filing cabinet.
That is a very apt comparison. However, while it is not a mainstream consumer staple you can buy at the grocery store, Miraculin has not been abandoned by the scientific or medical communities. Today, there is ongoing, highly promising clinical research into its therapeutic applications.
Okay, before we dive into the clinical research, we need to pause and make something incredibly clear to everyone listening.
Absolutely.
A hard stop. We are reading and reporting strictly on published scientific literature and clinical studies. We are absolutely not providing health, medical, or dietary advice. We are not recommending the consumption of the miracle berry to treat, cure, manage, or mitigate any disease or medical condition whatsoever.
I second that entirely and forcefully. We are simply exploring the data published in peer-reviewed journals for educational and analytical purposes. If you have health concerns, you must always consult a licensed medical professional.
Thank you. With that mandatory and explicit disclaimer firmly established, what is the modern clinical research actually looking at regarding Miraculin?
One of the most significant and compassionate areas of research involves oncology, specifically addressing the side effects experienced by chemotherapy patients. A very common, highly distressing side effect of certain systemic chemotherapy regimens is a condition called dysgeusia. This is a profound, often debilitating alteration of the sense of taste.
I've read about this. Patients often report that water tastes like thick sludge, or that everyday foods take on a highly unpleasant, bitter, or intense metallic taste, like chewing on a rusty coin.
Precisely. And when everything you eat tastes like a rusty coin or bitter ash, you naturally stop wanting to eat. This leads to severe loss of appetite, dangerous malnutrition, weight loss, and a drastic decrease in the patient's overall quality of life during a period when their body desperately needs nutritional support to recover.
That is just awful. So how does the miracle berry intersect with this?
Researchers have been conducting clinical trials exploring the use of miracle berries to combat dysgeusia. By utilizing the taste-modifying properties of Miraculin, patients can consume slightly acidic foods or beverages that, through the berry's mechanism, mask the overwhelming metallic off flavors and replace them with a pleasant, intense sweetness.
Wow.
This process can temporarily restore palatability to food, making eating enjoyable again, and thereby encouraging better nutritional intake during a critical period of their treatment.
That is incredible. It's taking this bizarre biological cheat code and using it for a genuinely therapeutic quality of life improvement for people who are suffering.
Hmm.
And also saw several research papers in our stack regarding its potential applications for diabetes.
Yes, because Miraculin provides an incredibly intense perception of sweetness without introducing any actual sucrose, fructose, or caloric content into the body. It is a subject of intense interest for diabetic dietary management.
Right, because there's no actual sugar involved.
Crucially, because it is a protein and not a carbohydrate, it does not trigger a glycemic response or an insulin spike. It theoretically allows individuals with metabolic disorders to experience the psychological reward and satisfaction of sweet flavors without the dangerous glycemic load that causes blood sugar spikes.
It's fascinating research, but again, to our listeners, this is ongoing scientific inquiry, not a medical recommendation. But it just highlights the profound potential power of hacking our own sensory systems, which really leads us perfectly into the final phase of our deep dive today.
The philosophical implication.
Yes, because when you move beyond the intricate chemistry, beyond the commercial history, and beyond the clinical trials, the very existence of Miraculin absolutely shatters our everyday baseline understanding of reality.
If we connect this to the bigger picture, it forces us to step out of the laboratory and into the realm of philosophy. Specifically, it forces us to grapple with the philosophy of perception and a concept known as phenomenology.
Let's break down phenomenology. What is it, and how does a small West African berry manage to break it?
Phenomenology is a philosophical movement that focuses on the rigorous study of conscious experience and how we perceive the world around us. It argues that our entire understanding of reality is constructed exclusively through our sensory experiences, and therefore reality is inherently subjective.
Subjective reality.
Now, as humans, we naturally tend to operate under the assumption of naive realism, which is the unquestioned belief that the world is exactly as we perceive it to be. We firmly believe that a lemon is inherently objectively sour.
Right. If I walk down the street and ask 100 random people what a lemon tastes like, 100 people will say sour. It feels like an objective, immutable truth of the physical universe, like gravity.
But the miracle berry proves definitively that sourness is not an objective property of the lemon at all. The lemon simply possesses citric acid. Sourness is nothing more than a hallucination agreed upon by our biology.
A hallucination. That is a heavy word to use for taste.
But it's accurate. It is a purely psychological construct generated by the specific architecture of our gustatory system. By simply introducing a single, naturally occurring glycoprotein to the tongue, we can completely rewrite that construct in seconds. We prove that the flavor of the world is not a fixed property. It's entirely dependent on the microscopic, transient state of our own cellular receptors.
We think of our senses as clear glass windows looking out onto the world. But Miraculin proves our senses are more like a rendering engine, and that engine can be easily hacked. The physics engine of the game says acid, but if you hack the code, the rendering engine draws sugar on the screen. And if the code can be changed that easily, the reality we experience changes with it.
And if we connect this to the bigger picture of human psychology, it has profound implications. The mind-body connection here is incredibly visceral. Taste is not just cold, hard data. It is deeply evolutionarily tied to emotional regulation, memory formation, and the fundamental reward pathways in the brain.
Because, from an evolutionary standpoint, sweetness implies dense calories, which means survival, which triggers a massive release of dopamine to encourage us to eat more. Conversely, sour or bitter implies unripe or toxic, which triggers psychological caution, defensiveness, or outright disgust.
Precisely. Taste dictates mood. By chemically altering a physical taste sensation, you're actively altering a person's cognitive and emotional state. If a person is eating something they expect to be painfully sour, their entire body braces for it. Their emotional state is defensive and anxious.
Like we talked about at the very beginning with the lemon.
Right. But when Miraculin forces that exact same chemical sensation to be registered by the brain as sweet, it triggers the brain's reward pathways instead. The anxiety is replaced with pleasure. By simply tweaking the folding of a single protein on the tongue with a slight shift in pH, we are completely rewriting a human's emotional and neurochemical response to a physical object in their environment.
It really embodies the idea of deep biological interconnectedness. Our internal emotional reality, our mood, our sense of comfort or pleasure. It can be entirely dependent on microscopic, transient environmental shifts in our mouth. A drop in oral pH of just 1.0 can literally be the difference between grimacing in pain and smiling in sheer delight.
It is the ultimate humbling realization for anyone who thinks they are in complete rational control of their experience. We are incredibly complex beings, yes, but we are also biochemical machines whose subjective reality is constructed, negotiated, and sometimes fabricated on a millisecond-to-millisecond basis by blind cellular mechanisms.
Wow. Okay, let's take a deep breath and try to recap this incredible journey we've been on today. We started on the coast of West Africa in 1725, observing the historical and cultural use of a small, unassuming red berry to alter the experience of eating.
And then we went microscopic.
We zoomed all the way down to the atomic level to examine a 191 amino acid glycoprotein called Miraculin. We watched it act as a biological sleeper agent, quietly binding to the human HT1R2, HT1R3 sweet taste receptor, specifically the venous flytrap domain, doing absolutely nothing at a neutral pH.
And then we introduced the environmental trigger. We introduced the acid. We watched the local pH drop, the positively charged protons flood in, and the highly exposed histidine residues undergo a violent, instantaneous conformational shift.
The activation code.
This transformed the passive protein into a powerful agonist that forcefully slammed the sweet receptor shut, sparking the G protein cascade.
We tracked that massive artificial sweet signal as it traveled up the cranial nerves to the brainstem. We watched the brainstem act as a bias gatekeeper, engaging inhibitory interneurons to actively delete the raw, burning sour signal from our conscious perception, proving once and for all that our brains are active editors, not passive cameras.
We explored how this astonishing biological mechanism was almost brought to the global masses by the Miraculin company in the 1970s, before being permanently halted by regulatory bureaucracy, leaving it as an object of fascination for sensory scientists and a potential future tool for clinical therapies in oncology and endocrinology.
There is a quote from one of our sources, an insightful article from the University of Toronto magazine, that I think perfectly encapsulates why we do this show. The author is interviewing a leading sensory researcher, and the researcher notes that learning this kind of dense microscopic sensory science actually gives the mundane, everyday world so much more meaning.
I love that quote.
He uses a brilliant driving analogy. He says that when you are driving a car, you don't have to physically see the corners of your rear bumper to know exactly where they are. Your brain seamlessly integrates the dimensions of the car into your own bodily sense.
The tool becomes an extension of your physical self through the power of sensory integration.
Exactly, and learning about the exact mechanisms of the miracle berry does the exact same thing for the simple act of eating. You now know that every single time you taste anything, a hot cup of coffee in the morning, a slice of pizza, even a cold sip of water, Your brain is actively, fiercely constructing that reality in real time.
It's all an active construction.
Millions of microscopic receptors are folding, opening, closing, sending millions of electrical pulses, and your brain is sitting at the switchboard, desperately deciding what you get to experience.
It transforms every single meal, every single snack, into a microscopic, breathtaking miracle of physics, chemistry, and neurology.
So I want to leave you, the listener, with a final provocative thought to mull over as you go about your day. We've just proven, scientifically and unequivocally, that your brain will gladly, instantly ignore raw, painful physical sensory data like sharp, burning acidity that is literally damaging your tissue, and it will gate it out of existence in favor of a louder, manufactured signal like sweetness.
It just throws the truth away.
If your brain is willing to do that with something as primal and basic as physical taste, what other sensory, emotional, or social realities is your brain currently gating out right now, simply because another signal in your environment happens to be louder?
It is a profound, somewhat unsettling question about the invisible blind spots in our own constructed reality.
Just a quick final reminder that absolutely no medical or dietary advice was given during this deep dive today.
Indeed, always consult a professional.
Think about all of this the next time you hold a raw, heavy, bumpy lemon in your hand, knowing that hidden deep inside the microscopic architecture of your own tongue is the latent power to turn that biting, violent acid into the sweetest honey.